We are here today at SKHS to answer the following question. Why does an infusion of TNF-alpha inhibit peripheral glucose uptake?
From our question, we define our mass as blood glucose. Blood glucose can be affected by either inflow, which is hepatic glucose production, which in the question did not differ between the blue TNF-alpha and the red control. It's also controlled by outflow, which is uptake into the skeletal muscle, where it was shown that there was a difference where TNF-alpha caused a decreased uptake compared to the red control.
We are now going to define the inflow of our model. So our inflow begins in the liver with hepatic glycogen. Hepatic glycogen is broken down into G6P via glycogen phosphorylase. From G6P, it breaks down to hepatic glucose via G6 phosphatase. And from hepatic glucose, it transfers into the blood where we have our final inflow and our mass, blood glucose. Now, due to the fact that there is no difference in blood glucose appearance between our control and TNF-alpha, we believe that TNF-alpha does not have a significant effect on our inflow.
To understand the outflow of blood glucose, we have to understand how glucose is transported into the skeletal muscle via GLUT4. So insulin will bind to the insulin receptor and activate this pathway to eventually activate AKT. AKT will remove AS160 from the GLUT4 storage vesicle, which will then be translocated to the membrane via RAC. Now, blood-free fatty acid can be transported into the skeletal muscle via CD36. Now, the accumulation of free fatty acids in the muscle will result in an accumulation of reactive lipid species known as ceramides and diacylglycerides. Ceramides will inhibit AKT, and diacylglycerides will inhibit IRS. This eventually results in a decrease in insulin receptor pathway activity, and therefore a decrease in GLUT4 membrane activity. Because during the TNF-alpha condition there is reduced glucose clearance, we assume that there is a reduced amount of GLUT4 transmembrane protein during this condition. Now, we hypothesize that TNF-alpha inhibits somewhere along the insulin receptor pathway. That could be either the insulin receptor, IRS, PI3K, or AKT. Now, it's also important to consider the fact that TNF-alpha could possibly increase the reactive lipid species in the muscle. However, due to the acute nature, we find it more likely that it directly affects on the insulin receptor pathway compared to the accumulation of reactive lipid species.
To test our hypothesis, we investigated a study by Palmgard et al., released in 2005. In this study, they used 9 participants, all men, controlled for weight and for height. The protocol of the study: first, all 9 men were given a tracer glucose infusion. An hour after, they were given either a saline, which was a control, or a TNF-alpha infusion. An hour after that, an insulin clamp was placed on them. This all lasted for 3 more hours. Blood samples were taken every 30 minutes, and muscle biopsies were taken at 0, 30, 60, and 180 minutes. In this study, they tested for hormones, metabolites, IRS, and a number of other factors.
So this study shows us that there was a decrease IRS1 levels in TNF-alpha, which also led to a decrease in phosphorylation of AS160 in the TNF-alpha condition versus the control.
Because TNF-alpha infusion resulted in decreased IRS1 activity, this supports our hypothesis that TNF-alpha inhibits the insulin receptor pathway. Consequently, this resulted in a decreased phosphorylation of AS160 and therefore a decreased GLUT4 membrane activity. This resulting decrease in GLUT4 activity from TNF-alpha results in a decrease of flow from our mass, blood glucose, to our skeletal muscle. This accounts for the discrepancy in outflow between TNF-alpha infusion and the control proposed in the question.